Okay, so we were working on number 55. We have 5 grams of aluminum pellets. They're at 100 degrees Celsius. The specific heat capacity for them is 0.89. We have 10 grams of iron, 0.45 specific heat capacity. Also at 100 degrees, we're going to dump them into this many grams of water, which has 4.19 specific heat capacity at 22 degrees Celsius. What will happen? Well, the good news is mainly I was making some dumb calculation errors. Hooray! But before we go ahead and try and solve this, let's just do a very quick review, okay? We talked about the difference between heat and temperature. Heat is energy. Energy is the ability to do work. So we're going to represent energy with Q in this case, is our heat energy. All right. And in general, like we said earlier, when we're talking about heat energy, rotate camera, we are actually not talking about just the temperature, which is the average speed of how fast the particles are moving around, right, in their random directions. We are also talking about the mass of the thing involved and the specific heat capacity. How much heat, how much energy can each gram thing hold for each degree of temperature, right? And that gives us the total energy available. Now, if we're going to talk about a reaction, whether it's a physical reaction where we're just dumping a bunch of hot pellets into water, or a chemical reaction where we're reacting things and the product is either giving off or absorbing energy exothermically or endothermically, well, in that case, we are not just talking about energy, we're talking about change in energy, delta Q in this case. So the delta of heat energy, the change that we see in a reaction, is going to be calculated by the mass. Well, that doesn't change, grams, right? At least not in a physical reaction. The specific heat capacity, how much for each gram can we hold in energy per temperature. Now, in this case, what's changing is the temperature, so delta T. Now, in this case, we have these two things, and part of the problem is we know that if we've got delta Q, the energy, the loss in energy by one thing, the loss, negative Q, negative change in heat energy, is going to be equal to the gain in energy by something else, right? Well, in this case, these two things, we're not just dumping them together, right? It's not that they are exchanging energy, and in fact, their temperature is the same. So the temperature wouldn't change. For these guys, we're putting them together in water. So we need to realize first that the energy total is going to be equal to the energy, in this case, from the aluminum, plus the energy, in this case, from the iron. All right? Well, that makes sense. Let's slide this down just a little bit. So if this is going to be the case, if the total energy is this, and we know that the energy is mass times the specific heat capacity times the temperature, well, then we can figure out that the total energy in this case, Q tot, I will say, is going to be the mass of the aluminum, 5 grams, times the specific heat capacity, 0.89 joules per Celsius gram, times the temperature. Well, in this case, we're actually not looking just for the total of energy. We're looking for the change in energy. So in this case, I'm going to go ahead and I'm going to say the change is the final temperature minus the initial, which is 100 degrees Celsius, okay? Plus, I really should have written this all over here. I'll change that in a moment. 10 grams, in this case of iron, times 0.45 joules per Celsius gram for the specific heat capacity of iron, times, once again, TF, temperature final, minus 100 degrees Celsius. Now, one thing I want to point out, this equation up here, the loss in energy from one side is the gain in energy from another. We're going to come back to that. And in particular, I want to point out right now before I forget, this side is obviously losing energy. Compared to the water, it is much higher temperature. It has more energy. It's going to lose some of that energy and give it up to the water. The question is, given the energy that the water absorbs, how much does its temperature change? So when we set this up, this should be our negative side because we know it's losing. In any case, now I've got something nice going on here. I have a similar term. So I'm going to pull that out and let's rewrite this. My change in energy total for the aluminum and the iron is going to be equal to, pulling this term out, temperature final minus 100 degrees Celsius times, this 5 grams times 0.89 joules Celsius grams plus 10 grams times 0.45 joules Celsius grams, right? And now I can just do the math here. 5 times 0.89, this is going to be what, 0.445 or 4.45, and then this is going to be 10 times 0.45 will be, just move that over 1, 4.5. 4.45 plus that is going to be 8.95 grams is going to cancel, and we're going to be left with joules, right, over degrees times temperature final minus 100 degrees Celsius. That is going to be our total change for these guys. Now, if we actually plug it in, we know that there is going to be no change. They start out at 100 degrees. They're going to end up at 100 degrees. We know that because I did it, because I'm very, very smart. All right, so now, though, we have a nice simple expression for what goes on with the metal guys in this part of the equation. So now we can say, all right, so these will be Q total, right? And this will be QH2O. Either way, we can go back to this and this. Our gain is our loss. And we know that this, ladies and gentlemen, is going to be our loss. So let's rewrite this now. I know that negative TF, and in fact, I can go ahead, I'm just going to distribute this right now. So 8.95 times TF, negative 8.95 TF, and I'm saying this whole thing is negative. So 8.95 times 100, but negative of that. So plus 895 joule degrees is going to be equal to this guy expressed as mass times specific heat capacity times temperature. And in this case, that's going to be what? Do the math here. We've got 97.3 grams times 4.19 joule gram Celsius degrees times, and we got to be careful. This is our initial temperature, not our final. So TF minus 22 degrees Celsius. Okay, just to do the math here really quick, we've got, clear that, 97.3 times 4.19 equals 407.687, so equals 407.687. Our grams have canceled out. Joule degrees times temperature final minus 22 degrees Celsius. We'll distribute that across. We get 407.687 is our temperature final in joules and degrees, minus 22 times 407. So going back to this, times 22 gives us 8,969.114 degrees, well, Celsius would cancel that, so joules, right? And actually, I should have done that up here, shouldn't I, when I multiplied this part across. So this is not joules Celsius, this is just joules. All right, so we have 895 joules, and all right, so now we just need to simplify this, and I'm going to do that by turning this off, moving it up. Our cameras and the internet, a wonderful thing. All right, so I've got a negative here, positive here, got a negative here, and a positive here. I'm going to start to simplify this by adding 8969.114 joules to both sides, 8969.114, and then I will also add 8.95 temperature final joules per degree plus 8.95 temperature final joules per degree to each side. All right, so let's do, this is going to cancel and this is going to cancel, so let's do this first. 895 plus 8969.114 plus 8969.114 is going to be, here we go, 9,864.114, and in that case that's joules, equals, and then we have to add 407.687 plus 8.95 joules per degree, and that gives us 416.637 joules per degree. And let's see, temperature final was, this is our temperature final. Okay, great. So now I just need to solve for temperature, right? Well, I can do that by dividing both sides by 416.637 joule degrees, and we know that that is the same thing as multiplying by the inverse, so 146,637. In this case, joules would go on the bottom, degrees would go on the top. This is great because it cancels out our units. And if we do the same thing over here, times 416,637 joules on the bottom, those will cancel, and degrees are left on the top, so I'm going to end up with the number, the degrees that I'm looking for. So I've got 9864.114.114 divided by 416.637, and I end up with equals my temperature final, because I've canceled everything else. I canceled my number is gone because itself over itself is 1. My joules are gone. My Celsius degrees are gone. Over here, joules are gone. I'm left just with a number of degrees Celsius. And in this case, is 23.675, blah, blah, blah. If we go back and check significant digits, I believe we're going to find that we have 3, in which case 1, 2, 3. This rounds this up, so 23.7 degrees Celsius should be our final temperature. And, well, heck, it's just a video. You can stop it right now. I'm going to double check if this, oh no! If this is wrong, it's going to be extremely embarrassing. But you know what, wouldn't be the first time. And so we are looking at chapter 6, number 55. That's captured. Yep, 23.7 degrees Celsius. So, that word number soup, it all really came down to recognizing this, right? And recognizing that the energy total that we were putting in on one side was just the sum of the two energies. We were able to solve and isolate our final energy in that case and plug it in on one side. Okay, so hopefully that helps a little bit.